Hi, Year 11, this is Mr. Lim here again, and this is our 6th video on the hydrocarbon series on geometric isomerism. Let's get started. Alright, so we're going to be learning about the differences between geometric isomerism and structural isomerism, and then being able to name stuff. Makes sense? Alright, so let's have a look. Hydrocarbons with double bonds are unique in the way that the double bond limits the movement of atoms around it, meaning that the two carbons across the double bond are held in fixed positions and cannot rotate. Okay, so our alkanes, the single bond between the carbon and carbons, can rotate, which means that like all of the atoms that are attached to those carbons can rotate around, but double bonds do not allow that rotation, right? Triple bonds don't allow that rotation either, but it doesn't really matter because a triple bond here is going to go lead to a single bond on either side, okay? And then that one can rotate. And then so if this one here can't rotate, but these ones here can rotate, it doesn't really make a difference because nothing can be actually attached to these carbons because that wouldn't be too many covalent bonds. There'd be 1, 2, 3, 4, and then you wouldn't be able to have another one over here, right? So alkynes also can't rotate, but it doesn't matter because there's not enough stuff to bond there, and therefore they can't really have geometric isomerism either. All right, so this inability to rotate means that a single structural isomer of certain alkenes can have two different versions based on the location of the double bond and the atoms bonded to them. All right, so structural isomers, remember, show the location of carbons and hydrogens and oxygens and stuff and where they are within the molecule. But then you could have two different structural, two of the same structural isomer, but two different shaped versions of them because the double bond can't rotate. Let's go walk through those ideas. All right. These are called geometric isomers. Geometric isomers have the same chemical properties as each other, but different physical properties due to the location of the atoms around the double bonds. All right, and then maybe I'll go through a couple of examples of that when we start drawing them out. So, for an alkene to have geometric isomerism, it must fulfill these criteria. It must be an alkene, duh. Right? The four atoms across the double bond, or the four atoms joined to the carbons in the double bond. Right? So 1, 2, 3, 4. Okay. So if you remember from year 11, these electron pairs will repel each other. These electron pairs here, 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 and here, and here will repel each other. So they form this little triangle shape here, right? Where they're trying to get as far away from each other, right? So these idea that this must be across the double bond, okay? Across the double bond means it's the ones that are in these four locations, okay? So let's have a look at these ones here. I'm going to be using the letters A, B, C, D to represent what the ideas are. So two atoms which are identical across the double bond. Now, two atoms that are identical, like, oops, don't want that. Okay, so A here and A here. These are identical and they're across the double bond. Okay, which means on one on either side. Okay, but if you had two identical which were not across the double bond, like over here, it's not going to have geometric isomerism. Okay, they have to have the two identical ones across the double bond. Okay, so that's that one here. And then two atoms which can be identical or non-identical to each other, but non-identical to the two atoms across the double bond. So you could have a B and a B here. Alternatively, you could have a B and a C here. Right, and those would be, so this would be the non-identical to each other, right, but and also non-identical to the other two A's there, right? Now you may ask what happens if you have A, B, C, and D over here. That also can have geometric isomerism, but we're not going to go through the ideas about how to get there at this level. Okay, so let's go through some. Actually, let's just go finish this off and then we'll go through some ideas. All right, so if two identical atoms, that's the two A's over here. So let's go put those back in as A's. Okay, if the two identical atoms are on the same side of the double bond, so same side means this side here, so this is what we're talking about, this arrangement where we're on this side here and this side here. Alternatively, it could also just be the two bottom sides as well. All right, so if they're on the same side of the double bond, it's called a cis isomer. And a cis prefix is added to the very start of the name of the hydrocarbon, right? And if the two identical atoms are on different sides of the double bond, then it's called a trans isomer, right? So this diagram here is currently a cis isomer, but if I was to get rid of this A here and this C here and swap its locations, right? If I put the A here and the C here, this would be the trans isomer. Oops, the trans isomer. So that's what we're dealing with here. Like just the swapping of the A and the C around changes the properties of it, right? And changes the identity of it. So that's why these are geometric isomers, right? Let's go draw a couple of very simple hydrocarbons here. Let's do HCH3, CH3, right? And we might go over in class why that CH3 is written like that. That's something that's important in year 12, right? So let's have a look at what we've got here. I have two identicals and two which are non-identical to the identicals but identical to each other. All right, that's perfectly fine. And so the two identical atoms are on different sides of the double bond, so this is the trans isomer. Okay, and this more importantly is trans 2-butene. Okay, so longest carbon chain is 4, right? So it's a but. The location of the double bond is on number 2, and it is a trans variant of it because it has the two hydrogens or the two identical things on opposite sides of the double bond, right? At opposite, I mean up or down, that kind of stuff. Now, this version here, the trans isomer compared to the cis isomer, which I'll just draw in now. Okay, the cis isomer, which would have the H over here and the CH3 over here, and now this is the cis isomer. Come on. The cis isomer, right? So these will have different physical properties, not chemical properties. Now the idea is that there is the majority of the substance on one side, okay? Which means that it'll have a polarity because this one here effectively unbalances or makes the molecule non-symmetrical. And as soon as it's non-symmetrical, then it will have two poles, and therefore it's going to have dipole-dipole rather than just in dispersion forces. So it's going to have dispersion and dipole-dipole, right? However, if you go back to the trans isomer, I might just redraw out a trans isomer, right? A trans isomer, if I just quickly draw that out, trans isomer is going to have only dispersion forces because this is still a fairly symmetrical substance. And so the idea is that this one here would have a higher melting boiling point because it is got dipole-dipole and dispersion forces, whereas this one over here only has dispersion forces, and the dispersion forces are going to be equally sized for both substances considering they are the same size. Right, let's just do one more example of a cis or trans isomer. Okay, so if I did propene, can this have cis or trans isomerism? Right, no it can't, because you have at least another one of these is identical to the other two, so therefore you're not going to be able to have cis and trans isomerism. And as soon as you see two things that are identical on the same side, as in like left and right, you're going to have no geometric isomerism. All right, so let's just redraw something else. Okay. Here we go. Okay, this is a 2-pentene, 5-chain long. Its double bond is on the second and third carbon. Okay, and this is the trans isomer. Right, because you've got the hydrocarbon, the hydrogens of the two identical substances on opposite sides of the double bond. All right, and so that's how you do this one. All right, we'll go through examples in the class. Adios.